This is a quick lesson on optimization for functions of several variables. Our outcomes are the following. By the end of this lecture, you will be able to find and classify critical points of functions of two variables, find the absolute maximum or minimum of a function in a closed region, and apply our optimization theory. Here are our objectives. We're going to take a quick review of Calculus 1 optimization. We're going to extend our theory to multivariable functions. We're going to apply the second derivative test for our optimization in multivariable functions. We're going to take a look at several examples. We're going to find and classify critical points. We're going to have an example where we're looking for the local extreme on a closed region using the extreme value theorem. And we're going to optimize a geometry application. Just a quick glance back at the Calculus 1 definitions. An absolute maximum of a function at C says that the function evaluated at C is bigger than anything that you can put into the function as long as x is in some domain D, and the minimum is similar. We also have a local maximum that says if we're looking at C as a local maximum, then we're just focused on the other points near C, and that provides our local maximum and minimum. And then we have Fermat's theorem. It says if f has a local maximum at C, then the derivative exists. Then the derivative has to be equal to 0. So that's kind of like our critical points. Now, this does not imply that if your derivative is equal to 0, then you have a local max or min. In fact, there are a couple of examples. One in particular, the x cubed function, has the first derivative at 0 is equal to 0, but it's neither a max or min. And so there's that appropriate warning. What is important about Fermat's theorem is that it's looking at the first derivative when the first derivative is equal to 0. That's a good place to start. Now, that leads us to the definition of a critical point. Critical point is when the derivative is equal to 0 or the derivative does not exist. And then we also have this other statement in the textbook that says if you have a local max or a min, then C is a critical point. All right. Absolute max and min. Absolute max and min is led by the extreme value theorem that says if you have a closed interval AB, then you're guaranteed a maximum or minimum, whether that be a critical point or the endpoint that attains that max or min. You're guaranteed it. And so there's a simple process for finding the absolute max and min, and that is to find the critical points and then find the values at the critical points, find the values at the endpoints, and then compare the largest and the smallest. As a quick example, here's an example where on a closed interval you attain your max at the endpoint, you attain your minimum at a critical point. And so you can just never tell whether your max will be at the end point or a critical point or your min. So we have to account for that. We also have tests for local max and min, and it's based on finding the critical points. And the first thing, or the tool that we use the most in Calc 1 was the first derivative test. And the first derivative test says basically if you go up and then you go down, if your slope is increasing, then it decreases. After a certain critical point, then you have a maximum. The second graph here is an example of a minimum. And then you have graphs where you're increasing critical point and continue to increase where that point is neither a max nor min, and same for decreasing. Now the advantage of doing this is that you're guaranteed to figure out whether you have a max or a min at your critical point, and that works really well if your domain is one-dimensional. We saw that dealing with limits, we can just look at from the left and from the right, but then when we extend that idea to multivariable functions, it doesn't quite work so well. So the first derivative test for us will not work very well for our purposes in studying multivariable functions. So we're going to scratch this out and go into a different test, and the other test is called the second derivative test. Now you have to be careful that this is not a test for inflection points. It's not a test for concavity. So a test for concavity is when we use the second derivative to find out the change in concavity and find the inflection points that way. So this is an example where 0 and 2, x is equal to 0 and x is equal to 2, are when the second derivative is equal to 0 and we see changes in concavities between those intervals. This is not the local maximum test or minimum test. It's not the second derivative test. So let's go back to the idea of the second derivative test. And for the second derivative test, what you're actually doing is you're finding out your critical points. So if we take a look at the first derivative here, critical point is when x is equal to 0 or when x is equal to 3. And so we're going to take those points 0 and 3 and put it into the second derivative. When we put 0 into the second derivative, we get 0. When we put 3 into the second derivative, we get a number that's bigger than 0. So if you have a number bigger than 0, we have a local maximum. I'm sorry, if you have a number bigger than 0, you have a local minimum. So there's local minimum. And when it's equal to 0, unfortunately, you don't have any conclusions. And so we see that sometimes the second derivative test, the test will fail and not give us any information. All right, so let's keep that in mind when we go into multivariable functions. Let's start the multivariable function study with some definitions, and this is a definition for local maximum and minimum. It says that your function evaluated at some AB point is going to be bigger than any f of x, y that's near that point, and then for an absolute maximum, it's going to be in some domain. So compare the local maximum and absolute maximum definitions. All right. Now there's a theorem that says if f has a local maximum at the point AB, the first order partial derivatives exist and are equal to 0. So this is again similar to a theorem that we've had in one dimension, but it's slightly changed a little bit because in 2 dimensions we're looking at the partial derivatives with respect to x and with respect to y. And so for that, they both have to be equal to 0. So that leads us to our definition of a critical point. A critical point is a point AB where the first order partial derivatives for both x and y, the partial with respect to x and the partial with respect to y, is equal to 0 or does not exist. Now they both have to be satisfying the critical point, both the partial with respect to x and the partial with respect to y. Otherwise it's not a critical point. Now back to the idea of the second derivative test. The second derivative test is a little bit more complicated. It's not just when the second derivative is equal to 0, or I'm sorry, it's not just when the second derivative is bigger than 0 or less than 0. Here, since our second derivatives are a little bit more complicated, in fact there's 4 of them. There's fxx, fyy, fxy, and fyx. Then we need to take a look at a different second derivative scenario. The one fortunate thing is that fxy and fyx should be equal to each other because we're dealing with nicer functions. And so here is what they're calling the discriminant that we're going to look at. And we're going to look at the sign of this, whether it's positive or negative. A couple of notes. In case C, when the discriminant is less than 0 and it's not a local max or minimum, this is called a saddle point. Also, if d is equal to 0, kind of like the second derivative test from calculus 1, if d is equal to 0, then that gives us no information. And then just a slight hint about trying to make this manageable for us instead of trying to memorize this formula. If we look at this discriminant, fxx times fyy minus fxy quantity squared, if we take a look at that as a matrix of partial derivatives, then it'll be easier to remember that term. Let's take a look at an example. We're going to classify critical points. So we have our function is 7 e to the y times y squared minus x squared. And so for us to find the critical points, we need to take the derivative and set them equal to 0. So the derivative with respect to x is a little bit easier because y is a constant, and then the derivative with respect to y will require us to use the product rule. And so what we're going to do is that we're going to set them equal to 0, and there are several ways to approach this, and one way is to set one of them equal to 0. We'll set fxy equal, or fx equal to 0, and we see that the only way that'll happen is when x is equal to 0. And what we can do is take this x value and put it into the fy value, and then set that equal to 0. So when we put 0 in for x, and set fy equal to 0, we see that y is equal to 0 and y is equal to negative 2. So that's going to give us two critical points. Critical point where x is equal to 0 and y is equal to 0, and a critical point where x is equal to 0 and y is equal to negative 2. So it might be good for us to also find the z values for them. So if we put 0, 0 into the original function, we should be able to get 0. If we put 0, negative 2 into the original function, we're going to get 28 e to the negative 2. So now that we have that, we need to classify our critical points. And so let's take 0, 0 first of all, and try to figure out what happens to the discriminant when we put 0 in for x and 0 in for y. So we need to find our discriminant, we need to find our second order partial derivatives, and here they are. We find the discriminant, and discriminant simplified would look something like this. And so now we put 0, 0 in there. So let's put 0 in for x, 0 in for y, and we get a negative number. So when our discriminant is a negative number, let's take a look at that again. We have the option number C, where it's neither a local max or min. So if you remember, that was a saddle point. So we have a saddle point at 0, 0, 0. So that's our saddle point. Alright, now we need to put in 0, negative 2 into the discriminant, and we see that that's going to give us a positive value. Now, positive value, I think when the discriminant is positive, we have one of two choices. We have to look at fxx and see if that's bigger than 0, we get a local min. If that's less than 0, we get a local max. So let's put 0, negative 2 into our fxx term, the negative 14 e to the y. We put negative 2 in there. That's going to be e to the anything is positive, and then we have a negative 14. So this is less than 0, and if it's less than 0, we see that it's a maximum. So we'll take that value, put it into the function, and then our output. Here they're only looking for the maximum value, not the actual point, but the value. So the value is when you put in to the equation. Notice we didn't have any local minimums here. So let's see how this is going to look like in the graph. I just typed in this equation into the 3D plotter, and this is what I get. So that's kind of hard to see, and I can't turn it using this static picture. But what you can do is take a look at some level curves. And when we took a look at some level curves, I noticed that there is this point over here, 0, -2, that gives us, looks like holes and stuff like that. And that is actually going to be a local maximum. And then over here we get that X drawn over here, so that's usually the sign that we have a saddle point. And so let's take another look at this using our level curves, and then we see that our saddle point is at 0, 0, and our local max is when X is equal to 0 and Y is equal to -2. Now let's take a look at the extreme value theorem for two variables. Basically, if you have a closed set D, then you're guaranteed a maximum and a minimum in your domain. And so if you compare that to the extreme value theorem back in Calculus 1, it's essentially saying the same thing. One thing I do want to take a look at is in Calculus 1, all we have to do is find the critical points and find the endpoints, plug in those values, and then the largest values are the absolute max, the smallest values are absolute min. So it's going to be very similar. Our technique for doing this in several dimensions is essentially find the critical values that are in the domain and find the extreme values on the boundary. Now unfortunately it's not just two endpoints like we had on an interval situation. This is a boundary that we're looking at, and that's two-dimensional. So we can either look at lines or circles or parts of curves, but we need to take a look at the boundary. So we'll see how to approach that. Here's our example. We have x squared plus y squared plus x squared y plus 7 as our function, and then our domain is a square boundary. Absolute value of x less than or equal to 1 says that we're having our x values go between -1 and 1, or y values go between -1 and 1. And so we're asked to find the absolute maximum and minimum values. So let's take a look at our function, and our first step is to find the maximum or to find the critical points. So let's take the first derivatives, fx and fy, and then we're going to find the critical points where both are equal to 0. So again, I'm going to set fx equal to 0, and here I have a situation where I have 0, either x is equal to 0 or y is equal to -1. So I'll take those in turn. Let's take 0 first when x is equal to 0 and put that into the fy equation, set that equal to 0, and we see that y is equal to 0. So it looks like 0, 0 would be a critical point. Now let's take y is equal to -1 and put that into the fy, set that equal to 0, and I get an x value of plus and minus the square root of 2. So we're going to end up with 3 critical points, 0, 0, and if I put 0, 0 into the original function, I get 7, root 2, comma, -1, back to the original function, I get 8, and then I get another 8 for the other one. Now let's take a look at our domain, our D. So that is going to be a 2 by 2 square centered around the origin. And one thing to note is that square root of 2 is like 1.5, 1.57 or something like that. So we're out of the domain. So for us, we can just cross that out and not worry about it anymore, because we're not going to bother with that. That's not part of our domain. So now we have a critical point 0, 0, 7. We got the value of 7 there, and so we just need to figure out the boundaries. So since this is a square, we have to express this as 4 lines and take a look at it line by line. Let's take a look at the first boundary where x is equal to -1 and y is going to be a value between -1 and +1. And when I take the derivative of that with respect to y and set it equal to 0, and I put -1 in for x, a fixed constant, I get y is equal to -1/2. And so that is going to be a point in the boundary that's a possible maximum or minimum. And so we'll mark that point, save that point for later. Now let's go to the next boundary where x is equal to 1, y is varying again. So we'll take a look at when x is equal to 1 in the original function. Now it's only a function of y. Take the derivative with respect to y, set it equal to 0, and you get y is equal to negative 1/2 again. And so when x is positive 1, y is equal to negative 1/2. Put that into the function, and you get 7.75. And so now we have two possible points. We keep going. One more boundary point to take a look at, or two more boundaries that we need to take a look at. When y is 1 this time, y is positive 1, I get put y is equal to 1 here and take the derivative with respect to x, and then you get 4x, and then set that equal to 0. So x is equal to 0, and then that's another possible point, 0, 1, and then you put that into the original function, you get 8. And so what happens when we take a look at the boundary, y is equal to negative 1. When you put y is equal to negative 1 in here, you're going to get a fixed value of 8. So that is not going to give us any critical values, although this whole line, we can see that this whole line has a constant height of 8, constant y value of 8. And so as long as our maximum is bigger than 8, we can eliminate that. But if it's actually equal to 8, so far we have 7, 7.75, and 8, it looks like this might be a candidate. This whole line, all these points on this line, might be a candidate for a maximum. Okay, so we took those derivatives over here, and then we found these values, but then we still need to take those corners, because we kind of didn't consider those corners. So what happens when x is equal to negative 1 and y is equal to negative 1? What happens when x is equal to positive 1, y is equal to negative 1, and basically 4 points that we want to put into the function. So let's put those 4 points in the function. At negative 1, we get 8. Negative 1, positive 1, we get 10. And then we got 8 and another 10. So it looks like we will have our maximum values to be 10. Just to summarize though, and let's remember that we also had the critical point, and comparing all these y or z values for these critical points and the endpoints over here, we see that the maximum value looks like it's going to be 10. And then the minimum values, it looks like it's going to be 7. Let's take a look at the graph real quick. A quick sketch of this would look like this. Probably want to zoom in a little bit. We also need to cut this in a domain. So we need to cut this in a domain where x and y are between negative 1 and positive 1. That's kind of hard to see. Let's see if we can get another view. Let's actually take a look at the surface where it's just that piece that's restricted to that domain, and here's a close-up of that. So this is what we have. What do we have here? We have the negative 1, negative 1/2, and a z-value of 7.75 happens in a couple of places. It happens on the boundary where the graph kind of dips down, and that's where we see it. Also, the other boundary, we saw that 0, 1, and 8 gave us a minimum, or gave us a critical point of with a z-value of 8. Remember that line where it's constant at 8? So here's that line over here. And more importantly, the maximum values happen at the corners, and then the minimum value happens at the critical point. So those are our absolute max and mins within this closed domain. One last example. Let's do an example using an application to geometry. It says find the equation of a plane that passes through the point 1, 3, 4 and cuts off the smallest volume in the first octant. So this is kind of a tricky problem. Let's take a look at this. visually, if we can take a look at that point 1, 3, 4 over there, and a plane that passes through that point. This is just one example. There's several of them, an infinite number of them, I guess, to be precise. And what we're interested in is that as we change the plane, the volume of this tetrahedron is going to change. And so we're kind of interested in finding the volume. So how are we going to find the volume? Let's see. If we let the x-intercept and the y-intercept and the z-intercept equal to alpha, beta, and gamma, then the volume of this thing will be kind of like alpha times beta times gamma. That'll give us a cube or a box, and I think this is going to be 1/6 of that box. So here's the volume of the tetrahedron with right angles, or one right angle corner. So what do we need to do? We need to find the equation of that plane. And so an equation of the plane is ax plus by plus cz is equal to d. Now, if we have alpha and beta as the x and y intercepts of that plane, and then gamma as a z-intercept, but if we let alpha and beta be varying, and then we can see that that gamma will have to change with respect to alpha and beta. So we're on our way to create a function of alpha and beta of two variables. So first we need to create that plane, and so let's say that alpha and beta are points that are on the plane, which they are because they're intercepts, and then we have the point 1, 3, 4 as another point on the plane. If we draw a vector connecting 1, 3, 4 and alpha 0, 0, and another vector connecting 1, 3, 4 and 0, beta 0, then we have two vectors that are actually on the plane. And we know that when we have two vectors that are on the plane, if we cross them, we will get the vector perpendicular to that plane. So we have alpha minus 1, negative 3, negative 4, and negative 1, beta minus 3, and negative 4 as our two vectors. If we cross those two vectors, we will get the perpendicular. And then if we just use that information to find the equation of the plane, it's going to be the first component of the normal times x, the second component of the normal times y, and the third component of the normal times z is equal to those components again dotted with any of the points that are on the plane. So we could choose 1, 3, 4, we could choose alpha 0, 0, we can choose 0, beta 0. So in this example I use alpha 0, 0 to help me find our d for the equation of the plane. Alright, so now that we have the equation of the plane, we need to express this as a function. We don't know what gamma is. In fact, we're going to write this equation, the volume, with a gamma in it. So we need to solve for gamma. And gamma, if this is the point 0, 0 gamma in your equation, if we put 0 in for x, 0 in for y, and gamma in for z, we should get this equation to be a true equation. So if we do that, we put 0 in for x, 0 in for y, we're going to get the z component, which is gamma, and then we're going to get gamma is equal to this. So now we need to write our volume as a function of two variables, as a function of alpha and beta. Our volume is going to be 1/6 times alpha times beta times gamma. Now the 1/6, I suppose we can leave it there or not leave it there. It's just a constant anyways. And so maximizing the volume here, that constant won't be that important for us. All right. So now let's take our equation, and we're trying to maximize this or minimize this. We're finding the smallest volume. We're trying to minimize this, so we need to take the derivative and set it equal to 0 to find the critical points. If we see that the derivative with respect to alpha is going to be a quotient rule. Also with respect to beta, it looks like it's going to be a quotient rule also. So let's be prepared to do a lot of tedious work and just be careful with your algebra. So let's take the derivative with respect to alpha, and let's say simplified, it looks like this. I think the 1/6 came back here. Again, constants aren't really that important. And if we take the derivative with respect to beta, we get something similar to that, and then now we're going to set it equal to 0. And when we set it equal to 0, let's set the first one equal to 0, v sub alpha equal to 0. That's just equivalent to the numerator being equal to 0. And then if we solve for alpha, you're going to get something with a beta in it. So alpha is equal to 2 beta over beta minus 3. Now we need to take that information and hold on to that information for a minute and take the derivative with respect to beta, set that equal to 0. We're going to get this equation over here. And now we'll take this information that we got from alpha and put it in for alpha into this into the second equation. And so in effect, we're trying to figure out alpha and beta where both v sub alpha and v sub beta is equal to 0. So if we do that, all the alphas are gone, just a function of beta. Let's solve for that by finding common denominators, beta minus 3, and then combine the numerator. And then we're going to set the numerator equal to 0. The denominator, beta, when beta is equal to 3, then it's going to be undefined. But we're just really concerned about the numerator. So let's let beta equal to 9 in this case. And so that's just one value. Let's put the beta equal to 9 back into the alpha equation over here. And then we're going to get the pair. Alpha is equal to 3 and beta is equal to 9. So that is our critical point. So if we actually want to find our plane, let's just take our alpha is equal to 3 and beta is equal to 9 and put that into our plane equation. And that gives us 4 times 9x, 4 times 3y, and then this big mess times z. And that is simplifies to this. And then if we could just plug that in, I suppose, but it looks like they all have a factor of 3 involved. So let's divide out by 3, and then we get a simpler form of the line. So our equation of the line is 12x plus 4y is equal to 9z. All right, so that should do it, and that's our quick example for maximums and minimums. Okay, good luck.